Relativistic Momentum and Energy by Ayla, Callista, and Savita. Before we explain relativistic momentum, we must first understand the theory of special relativity, which explains that the speed of light is the same for all observers, even when they are moving with respect to one another. Isaac Newton's equation for momentum is the product of mass and speed. However, this equation is not accurate for objects traveling at speeds above 0.1 c, or close to the speed of light, as it does not take the effects of special relativity into account. The momentum of an object that travels at speeds near the speed of light is called relativistic momentum. Einstein formulated a new equation for momentum, P equals gamma mv, to account for the relativistic effects on momentum, where m is the rest mass, v is the speed, and gamma is the relativistic factor, 1 over the square root of 1 minus v squared over c squared. Rest mass is the inertial mass of an object measured at rest with respect to the observer. In special relativity, this value is invariant, meaning that it does not change as speed changes. It is important that rest mass is used to calculate relativistic momentum because an object that travels near the speed of light will have a different measured mass.
This graph shows that momentum will increase linearly with speed when Newton's equation is used. However, when special relativity is considered, momentum will approach infinity as speed approaches the speed of light. The conservation of momentum states that the total linear momentum of an isolated system remains constant at all times when there are no external forces acting on the object. This concept applies even with the effects of special relativity. However, when an object approaches the speed of light, Newton's equation for momentum is not conserved in all inertial reference frames. Thus, in order to conserve momentum, relativistic momentum must be used instead. In Newtonian physics, work is equal to the change in kinetic energy. In this case, the mass of the object always remains the same, while its velocity changes to accommodate the energy being transferred. However, these rules do not apply in situations where special relativity must be considered. Einstein used the equations of special relativity to show that the total energy E of the moving object is related to its rest mass m and speed v by the following relation. Consider the special case in which the object is at rest. When v is 0 meters per second, the total energy is called the rest energy E, and the equation reduces to Einstein's now famous equation, E equals mc squared. The rest energy is the amount of energy an object at rest has with respect to an observer, and it does not change.
When an object is accelerating from rest, it acquires kinetic energy in addition to its rest energy. The total energy is the sum of the rest energy and the kinetic energy. Therefore, kinetic energy can also be written as a difference between total energy and rest energy, or mass times speed of light squared times 1 over square root of 1 minus velocity squared over speed of light squared minus 1. This equation is the relativistically correct expression for kinetic energy of an object in motion. For speeds much less than the speed of light, the relativistic equation for kinetic energy reduces to 1/2 mass times velocity squared. Thus, Mass-Energy Equivalence states that the rest mass of an object is equal to its energy. Since mass and energy are equivalent, any change in one is accompanied by a corresponding change in the other. Any change in the rest energy of a system causes a change in the mass of the system according to delta E is equal to delta m times speed of light squared. But in most instances, the change in mass is too small to be detected. To see that the speed of light as a universal speed limit is a consequence of special relativity, consider the following equation. As velocity approaches the speed of light, the relativistic factor approaches 0. Hence, kinetic energy becomes infinitely large. However, the work energy theorem states an infinite amount of work must be done to give the object an infinite kinetic energy. Since an infinite amount of work is not available, objects with mass cannot attain the speed of light.